In this example, we're going to find a fourth degree polynomial and we're going to use it to approximate arctan of 6x. Now, when we do this, we have to use a method called Taylor expansion. And this is going to let us create a polynomial with infinite number of terms, and the coefficients of those terms, they're going to be derived from the derivative of arctan 6x. So this n right here means the number derivative. So for example, if this said 2, when I plug in 2 for n, this would be the second derivative of f. A is our center, and we're given that our center is at 0. I just have x raised to the nth power. So I need to find all the derivatives first. So I'll let you do the intermediate step, but I did the derivatives out ahead of time to save some time. And these are the derivatives that I got up to the fourth derivative. Now I knew I had to go up to the fourth derivative because we're doing this for a fourth degree polynomial, which means my n is going to go from 0 to 4. So the last n that I plug in is 4. So that's where I stop finding derivatives. Then what we have to do to finish getting this expansion, we have to evaluate all those derivatives at our center. A is equal to 0. So we're going to plug in f of 0, f prime of 0, and that's going to come with an x because when we plug this in for n, that's going to give us, so x to the first power. And then we have the second derivative evaluated at 0, and then we get an x squared here because this would be a 2. And then this gives us the fourth derivative evaluated at 0. And then this exponent is 4 because n is 4, that's where we stop. So that's our last exponent. So now we have to evaluate the function and all the derivatives at the center, which is 0. So when I plug in 0 for my function f, plug it in here, and I get the inverse tangent of 0 is 0. So this term is going to be 0, and I have that listed here. So this is when n is equal to 0. Then when n is equal to 1, that would be our x to the first, and to find our coefficient, we plug in 0 into the first derivative and divide by 1 factorial, which is just 1. So when we plug in 0 into the first derivative, we get 6. So we have 6 over 1, which is just 6. And so that's why we have 6x here. That's our x to the first term. Now, when we look at our term for the second derivative, when I plug in 0, this whole thing is going to disappear when I plug in 0 for x because this in the numerator is just going to make everything 0. So for the second derivative, this all disappears. Whoops, this should be squared. I messed up when I typed this. So change this to a 2 because this is when n is equal to 2, so we should have degree 2 there. Now for degree 3, when I plug in 0 for the x's in the third derivative, we're going to get out negative 432. So when I plug in negative 432 here in the numerator, we get negative 432 times x to the third divided by 3 factorial. 3 factorial is 6, so we have to take the negative 432 and divide by 6, and what we get, negative 72, and that's our x to the third term. Fourth term is going to be the same thing as the x squared term. This is just going to disappear. When we plug 0 into the fourth derivative, because of this x right here, that's going to make everything 0. And then when we put it on top here to replace that fourth derivative, we're going to get 0 times x to the fourth over 4 factorial. So this is going to be 0x to the fourth. Now when we get rid of the zeros, what we're left with is 6 minus 72x to the third. So when we plug in values that are close to 0 for x, we can use this as an approximation for the inverse tangent of 6x. So looking at the inverse tangent function and the Taylor polynomial that we found that's supposed to estimate the arctan. So here's our arctan in black, and the polynomial we came up with to estimate arctan near 0 was this cubic function. I wanted to show you how close this is, so I zoomed in, and that's this picture here. If I plug in anywhere in this vicinity, any value of x, into our polynomial, then we're going to get a really, really good estimation for the arctan of 6x.